Hello students, in this module we are going to cover topics under vector and three-dimensional geometry. With computation point of view, these topics under vector and 3D geometry are generally easy, and many students leave these topics, but it's like low investment and high profit scheme to study these topics. Okay, so we will be first looking out the concepts of this and then solving the problem, right? So let me start with vector. Say if there are n vector a1, a2, a3 dot dot an, so we define linear combination of these vector n vectors as vector r. So vector r can be written as k1 a1 plus k2 a2 plus dot 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 kn an, where k1 k2 k3 dot 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 kn are all real number, right? For example, say we have a vector a1 as say 2i plus 3j, okay, and a2 as 5i minus 6j. So linear combination of a1 and a2 can be written in form of k1 a1 plus k2 a2, where k1 and k2 are any constants. For example, if we take k1 is equal to 2 and k2 is equal to minus 1, so its linear combination will give another vector which is equal to 2 times 2i plus 3j minus 1 times 5i minus 6j, which is equal to minus I, which is equal to 2 times 2 4 minus 5 minus I, and 3 times 2 6 plus 6 plus 12j, right? So linear combination of this and this vector with k1 is equal to 2 and k2 is equal to 1 will result another vector which is equal to 2. So why this linear combination is important? Let us see that. Suppose two vectors are collinear. Collinear means they have same direction. Say this is vector a1 and this is vector a2. Okay, then a1 can be written as ka2, isn't it? We can write vector a1 as k times a2. That means linear combination of vector a1 and a2 is 0, can be 0. That means vector a1 and a2 are dependent vectors. So from here we define another term. If there are n dependent vectors, then their linear combination, there must exist k1 constants k1 k2 kn such that their linear combination is is 0. That is k1 a1 plus k2 a2 plus k3 a3 plus dot 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 kn an is equal to 0, where k1 k2 dot 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 kn are not all 0. Okay, that means if all are 0, then we cannot say whether it is linear. If all are 0, then vectors are independent, because these vectors does not depend on each other, right? But if they are dependent, then there must exist at least one value of k, non-zero value of k, such that this results to 0. Its linear combination is 0, right? So for two collinear vectors are always dependent. Similarly, three vectors which lie on a plane are always linearly dependent. Three vectors lying on a plane are always linearly dependent, right? Say this is a vector 1, this is vector 2, vector a1, say vector a2, and say this is vector a3. So we can have the values of k1, k2 and k3 such that its linear combination is 0, right? Say this is a1, we take this vector a2 here. I mean, we can travel this vector a1 from this position to this position parallelly, and say by multiplying some constant to a3, we travel this vector a3 here. Say a3 is somewhat larger. Let's say a3 somewhat like this. This is a3. Okay, a3 somewhat like this. So you will be saying that a1 plus a3 is not equal to a2. Now a1 plus a3 is not equal to a2 here. But if we multiply some constant in a2, say if we multiply some constant k such that a2 becomes this value, okay, this value, till this value, right? So that a2 becomes let me write in more fashionable way. Say we have vector a1 here, say a2 here, and say a3 here. Okay, so where we clearly, if we want to see whether they are dependent or not, okay, say we have a concept, three vector line on a plane are always linear dependent. So let us try to check this. Okay, so we have vector a1. Let us coincide the tail of a1 and a2. So if we travel vector a2 here parallelly, we will be getting this vector, right? And say if we travel, now let us coincide the tail and head of vector a1. This is vector a1, this is vector a1, and this is vector a2. So let us coincide the tail of a3 with head of a2. So it is something like this, say a3. Then we must have some multiple. There must exist some multiple k such that this must be ka3, right? So we have a1, right, is equal to a2 plus ka3, right? So from figure you can see that. So we have a1 minus a2 minus ka3 is equal to 0. So the linear combinations of a1, a2 and a3 is 0 for some value of k1, k2 and k3, right? So these are linearly dependent vectors. So vectors lying on a plane are linearly dependent. Okay. So now let's move forward. We have a concept of unit vector A. A unit vector is represented as A cap, which is equal to vector upon its magnitude. Okay. So we use unit vector to represent another vector in direction of that vector. Suppose this direction. Suppose this is the direction, and in this direction we define a unit vector A. So any vector, say we have to represent this vector. This vector we have to represent. Okay. So if we want to represent this vector, say, then this vector, if its length is say L1, then this vector can be written as L1 times A. Okay. So this is the concept for unit vector. Now addition and subtraction of two vectors. Just let us look the formula and parallelogram law of addition, you all know. Say this is vector A1, this is vector A2. Then adding these two vectors will. So parallelogram law of addition tells us that if A1 vector is like this and A2 vector is like this, then the sum A1 plus A2 will be somewhat here. That means diagonal of this parallelogram will be the sum of these two vectors. Okay, right? And similarly, subtraction means if we have to do A1 minus A2, then first we have to make this A2 vector as minus of A1, minus of A2. That means this is minus of A2. Okay. So A1 plus minus of A2 will be diagonal of this parallelogram, that is this vector. So this is A1 minus A2. Right? Okay, now moving to the product of two vectors. Two vectors. So two vectors, product of two vectors can be scalar as well as vector. So first we will be defining scalar product. It is also known as dot product. Say we have two vectors A1 and A2. Then we write as scalar product of A1 and A2 as A1 dot A2. And its value is magnitude of A1 vector into magnitude of A2 vector times angle between, cos of angle between A1 and A2. That means say if this is A1, this is A2. Say this is A1 vector, this is A2 vector, and this is angle theta. So A1 dot A2 is magnitude of A1 times magnitude of A2 into angle between these two vectors. So this is dot product of two vectors. In this concept dot product, we will be also looking at projection of one vector on another. Say we have to find, say this is vector A and this is vector B, and angle between them is theta. Say we have to find projection of A upon B. Projection of A on B. So if we check, then this length is the projection of A upon B. So projection of A upon B is nothing but magnitude of A into cos theta, right? So this can equivalently written as dot product of these two vectors A1 dot B upon magnitude of B vector, right? So knowing the dot product, we can easily find the projection of one vector on another. Okay. So now moving to second type of product, which is known as vector product or cross product of two vectors. So we have vectors say A1 and A2. We define vector product as A1 cross A2. So it is also known as cross product, as another vector, third vector B, such that say this is vector A1 and this is vector A2, and angle between these two vectors is theta. So A1 cross A2 will be another vector which is perpendicular to both A1 and A2. That is, either it is up or it is down the plane. So if it is up the plane, we denote it by a symbol like this, and if it is down the plane, we denote it a symbol like this. This means up the plane. This means down the plane. So we will get another vector whose direction is either up the plane or down the plane, depending upon A1 cross A2 or A2 cross A1. So if it is A1 cross A2, then we are moving from this side to this side. That means if we curl our finger, okay, right hand, using right hand, if we curl our all four fingers, then thumb will point in down the plane. So if it is A1 cross A2 here, then we will be getting the direction as down the plane. And if it is A2 cross A1, then if we will be curling our right hand fingers from A2 to A1, then the thumb will point in up direction. So we will be getting the direction as up. Okay. So let us define the direction of A1 cross A2 as a unit vector AN. Okay. Since this is B, let us write it as A1 cross A2, a unit vector in the direction of A1 cross A2, that is perpendicular to A1 and A2. We will say that unit vector is N. Okay. Then it will be along this N vector. Okay. Where N vector is either up the plane or down the plane, depending upon the relative position of A1 and A2. Right. So A1 cross A2, the magnitude of A1 cross A2 is defined as magnitude of A1 times magnitude of A2 into sine theta. Okay. And direction already we have explained what is the direction. So B vector is magnitude of A1 into magnitude of A2 sine theta, and in the direction of N vector. Okay. So this is defined as the vector product, or we call it as cross product of two vectors. Now if we see for three vectors, scalar product or dot product, then say for if vector, for there is a vector A, B and C, and we want to find scalar product of these three vectors, then how it is defined? Scalar product of these three vectors are defined as bracket ABC. Okay. Which is equal to A dot B cross C or A cross B dot C or C cross A dot B or C dot A cross B. That means either of these four we can write. Okay. See, this is B cross C will give another vector, and with it dot it always give a scalar quantity. So this bracket can be defined as this bracket. This bracket can be defined either of these four vectors. So basically we can write ABC bracket as BCA bracket also equal to CAB bracket. Okay. So we are not changing the relative position of A, B and C. Okay. We are just rotating A, B and C. Say A is here, B is here, C is here. A, B, C. We are just rotating A, B, C. We can take CAB, either BCA or ABC bracket. We will be getting the same throughout. So what does it mean? So we have three vectors. This is A, this is B, and say this vector is C, which is out of the plane. Okay. Not in the plane of A, B and C. Then A cross B dot C will give us scalar product of A, B, C. Okay. Which means that if we draw a parallelepiped, okay, this is a parallelepiped, right? With sides say if we draw a parallelepiped, this is parallelepiped, okay, and we have vectors. Say this is vector A, this is vector B, and this is vector C. Okay. then A cross B dot C will give volume of this parallelepiped. Okay. Alright. So this is all about the scalar product or dot product of three vectors. Now for vector product of three vectors, vector or cross product of three vectors. Say we have three vectors, vector A, vector B, and say vector C is out of the plane, something like this. So we defined cross product of three vector as A cross B cross C, okay, which is not same as A cross B cross C, okay. Remember it, because A cross B will give vector perpendicular to A and B, and we are taking that perpendicular vector with cross to C, and here we are getting B cross C as perpendicular to vector B and C, which we are again multiplying. That is, we are again finding the vector product of A and the perpendicular vector which is perpendicular, and a vector which is perpendicular to B and C, right? So we say that A cross B cross C, this will always give a vector which is in plane of B and C, because this is perpendicular to B and C, and say this is perpendicular to B and C in the direction of say n vector, which is perpendicular to B and C, where n unit vector is unit vector in direction perpendicular to B and C, okay. And we are again doing, and then we are again doing A cross n, okay. A cross n times say A is the magnitude of B cross C. So we will be getting vector perpendicular to A and n, vector perpendicular to A and n. That means the resultant is perpendicular to n, this vector. That means perpendicular of B and C. That means in the plane of B and C. So we will be getting, for this we will be getting vector in plane of B and C. Vector in plane of B and C. So we have A cross B cross C is something K1 B1 plus K2 B2, right? Okay. I mean K1 B plus some K2 C, okay. So we give value K1 as A dot C and K2 as minus of A dot B. So A cross B cross C is equal to A dot C vector B minus A dot B vector C, okay. So this is all about the vector. Now we are moving to three-dimensional geometry. In three-dimensional geometry we have three axes, x-axis, y-axis and z-axis, and unit vectors which are along x-axis is called I cap, along y-axis is known as j cap, and along z-axis is known as k cap, okay. So if we want to represent a point, say this point is 1, 2, 3 and this is origin. So position vector of this point can be represented as I plus 2j plus 3j, okay. So we are going to study this three-dimensional geometry by linking it with vector. Okay, so we have a point and we represent it as a position vector in vector. Okay, now let us recall all the formulas. Distance d, where d is the distance between 2 points. Distance between 2 points. 2 points x1, y1, z1 and x2, y2, z2. So d is given by x1 minus x2 square plus y1 minus y2 square plus z1 minus z2 square under root. Okay, or if we have position vectors r1 for x1, okay, and r2 for x2, then we have distance as r1 minus r2 vector and modulus of this vector, right? Okay. So therefore now we will be defining direction cosine. Okay. Say we have a point here, alpha, beta. Let us not write alpha, beta, gamma. Let us write it as x, y and z. So we define, this is point say P. So we define a direction cosine of line OP. Direction cosine of line OP as L, M and N. Okay, these are the direction cosines L, M and N, where L is equal to cos alpha, M is equal to cos beta, N is equal to cos gamma, where alpha is angle made by, say this is x axis, this is y axis and this is z axis. Beta is angle made by y axis and gamma is angle made by z axis. Okay, so we define direction cosine of line OP as cos alpha, cos beta, cos gamma. Okay, so from here, if OP, length of OP is r, then we have cos alpha as x by r, cos beta as y by r and cos gamma as z by r. So if we take a square of all these three quantities and sum it, then we will be getting cos square alpha plus cos square beta plus cos square gamma as x square plus y square plus z square upon r square, which is equal to r square upon r square, which is equal to 1. So sum of the square of direction cosine must be equal to 1. Okay. Now if we try to understand the physical meaning of direction cosine means unit vector in direction of any line. Suppose this is a line, okay, and if we have a unit vector, say we have a unit vector, Li plus Mj plus Nk in direction of this line, then direction cosine of this line is Lmnn. Okay, right? This is nothing but unit vector in direction of line, given line. Now we have another term, direction ratio. Direction ratio is some multiple times direction cosine. Direction ratio is some constant time direction cosine, say KL, KM, Kn. So we call it as ABC as direction ratio. If this is a direction ratio, ABC is direction ratio, then it means that A, B and C are some multiples of Lm and N. Okay, where K is same in all the cases. So we have different direction. We can have different direction ratios. If you multiply with some constant, any constant by if you multiply direction cosine with any constant, we will get a direction ratio, right? Say we have a direction cosine as 1 by root 3 1 by root 3 and 1 by root 3. Or let us not take these numbers. Let us take direction cosine as 1 by 2, 1 square plus 1 by 4 means let us take 1 by 3 here. So 1 by 9 plus 1 by 4 means 36, and this is 4 plus 9, 13 by 36. 1 minus 13 by 36 is 36 minus 13, 23, and 23 by 36. Okay, root under. So this is a valid direction cosine because this is square plus this square plus this square, this square plus this square plus this square is equal to 1, right? That's why we have done this calculation to make this square plus this square plus this square is equal to 1. So we have a direction ratio can have, if you multiply it by 3, then we will be getting 1, 3 by 2, 3 root 23 by 36. This is direction ratio. We can get another direction ratio. Say if we multiply it by 5, then we will be getting 5 by 3, 5 by 2, 5 root 23 by 36. So this is another direction ratio. These all are direction ratio. So we can have n direction ratios. That means infinite direction ratios for given direction cosine. Okay, or for a line, for a given line. But we have only one unique direction cosine for a given line because we will have a unique unit vector in that direction, and we can have n number of vectors in that direction. So we have n number of direction ratio. Direction ratio basically represent any vector in direction to that line. Okay, direction ratio represent any vector in direction to that line. Okay, say if ai plus bj plus ck is a vector in direction to this line, and this is a vector in direction to this line, then ABC is direction ratio of this line. Okay. One more thing, if say A1, B1, C1 and A2, B2, C2 are the direction ratio of same line, this and this are dr of same line, that means A1 by A2 must be equal to B1 by B2 is equal to C1 by C2, right? Okay, this must hold. One more thing, if we have direction ratio of a given line, then we can easily find the direction cosine, because say if one asks you to find a unit vector for a given vector, okay, then what you do? Say we have a vector ai plus bj plus ck, okay, the vector. So unit vector can be found out by vector divided by its magnitude. So what is its magnitude? Its magnitude is root under a square plus b square plus c square. So we can have this as a unit vector in direction to this vector. Okay, so this is direction ratio vector and this is a direction cosine vector. So we can, if we want to see what is direction cosine for given direction ratio, we can always find it. Okay, so L is basically this, M is basically this, and N is this, right? Okay, now moving toward the equation of lines, straight line. We've already defined direction cosine, so now straight line. Say we have a point and a direction cosine of a given line. Equation of straight line. Equation of straight line when a point on it and its direction ratio or direction cosine are given. Okay, so say this is a line and we know one point on a line. Say let us denote this point as P point, whose coordinate is say x1, y1 and z1, and let us say we know its direction ratio, which is a, b and c. That means a vector in this direction, which is ai plus bj plus ck. Okay, let us name this vector as vector m. Or let us name it as vector b. Let us name it this vector as vector b. B, capital B. Okay, capital B vector. Now we have to find moving point P dash x y z. Okay, so with these 2 points we can make direction ratio. Direction ratio is, with these 2 points we can always make direction ratio as x minus x1, x minus y minus y1 and z minus z1. This is the direction ratio, and we have a direction ratio ABC, which is also the direction ratio of same line. That means ratio of these two are equal. So x minus x1 upon a is equal to y minus y1 upon b is equal to z minus z1 upon c. This is the equation of straight line when a point on it and the direction ratios are given. Or in vector form, we can always write the equation. Say we have to find a moving position vector of x, y, z. So that position vector is r vector. So r is always, and this vector is say capital A vector. Position vector of point P is capital A. So r is always capital A plus some lambda times capital B. Okay. So this is in vector form. You can always write the equation. So basically we always write the equation of a straight line in this form. If we know the 2 points on a straight line, then we can first find the direction ratio and use this formula, right? Okay, so this is about the straight line. Okay. Now if we have a plane, equation of a plane in different form. So let us see what is a plane. Say in 3-dimensional geometry we define a plane like this. We have our coordinate system like this, and we have a plane like this. This is x, this is y, and this is z. Okay. So first we define a vector normal to a plane, or direction cosine of normal to a plane, or direction ratio normal to the plane. So we define a vector or direction ratio or direction cosine, okay, of line perpendicular to plane. Say that vector is n vector. Okay, n vector. Or we have equivalently its direction cosine as direction ratio as a, b and c. Okay, so if we have a vector which is say perpendicular to planes, then we will be getting many planes. Okay, we will be getting many planes. Okay, here, anywhere. Okay, so that this is perpendicular to this plane. So to fix a plane, to make a plane unique, we have to also give one more condition. Say we give a plane must pass through this point, then we can find the equation of the plane. So if we have, so let us find equation of a plane on which one point on it is given and its direction ratio of its normal line is given. Normal means perpendicular line. is given. Okay, so say this is a plane. Okay, this is our axis, this is the plane, and we know this vector n vector. Okay, and also we know a point on this vector. Say this point is vector a, whose position vector is vector a. Okay, and we have to find another vector, and we have to find a variable vector r, position vector variable vector r, so that we get a plane. Okay, we have this vector. Then if we subtract this vector, say this vector is r minus a, then r minus a vector always lie on this plane, always lies on the plane. Okay, so any vector which lie on the plane is always perpendicular to vector capital N, so their dot product must be 0. So r minus capital A dot n is always equal to 0. So this is the equation of plane in vector form. If we make it in Cartesian form, then r is a variable vector, that means its coordinate are xi plus yj plus zk, where x, y, z are variables, and a vector, say the point a is xi, x1i, x1, y1, z1, then a vector must be x1i plus y1j plus z1k. And n vector, let us name this n vector as ai plus bj plus ck, where abc are direction ratio of normal line. So we have r minus a as x minus x1 dot r minus a dot n as x a times x minus x1 plus b times y minus y1 plus c times z minus z1 is equal to 0. Okay, so this is the equation of plane in Cartesian form. Also we can find this is the general way in which we find the equation of a given plane. So let us find one more equation of a plane when unit vector in direction of its normal is given and its distance, perpendicular distance from origin is given. That means L, M and N are given direct. Unit vector means L, M and N, direction cosine. Direction cosine, that means direction cosine of normal line is given, perpendicular line is given, and distance of that plane with origin is given. Suppose this is our coordinate plane and say this is a plane. So perpendicular distance on this plane is say this distance. So this distance d is given, and unit vector in direction of this is given. Say this is n cap vector is given, because unit vector in direction of this vector is the direction cosine of line, perpendicular line, normal line, right? So position vector of this point can be written as d times n, isn't it? D times n. So we have r minus d times n into n is equal to 0, or we have vector r dot n minus d into n dot n is equal to 0, or we have n dot n is equal to 1. So we have r dot n is equal to d. So this is the equation of vector plane in vector form. And in Cartesian form, if we make it in Cartesian form, this is n cap, so this is li plus mj plus nk. So we have lx plus my plus nz is equal to d. Okay, right? So for general equation of plane, general equation of a plane. If we have a plane ax plus by plus cz plus d is equal to 0, right? Then a, b, c are direction ratio of perpendicular line. It's perpendicular line or it's normal line, right? We can have this information. And if we want to find the distance from origin, then we have to make this direction ratio, convert the direction ratio in direction cosine, right? Because here we have seen that if L, M, N are direction cosine, then D will give the distance of plane from the origin. So we have, if A, B, C as direction ratio, then if we convert this in direction cosine, then automatically this quantity will be giving the distance between origin and plane. So what is the distance between origin and this plane? So for making it ABC as direction cosine, we have to divide this ABC by its magnitude vector, that is under root a square plus b square plus c square. So dividing this whole equation by under root a square plus b square plus c square, we will be getting lx plus lx plus my plus nz plus d upon a square plus b square plus c square under root is equal to 0, right? Because L is nothing but a upon a square plus b square plus c square under root, similarly m and similarly n. So we have lx plus my plus nz is equal to minus of this quantity. So distance from origin can be written as mod of d upon a square plus b square plus c square, right? So if we have to find the distance between two planes, say distance between two parallel planes. So we have two parallel planes as ax plus by plus cz plus d1 is equal to 0, and another parallel plane, because since these two planes are parallel, so direction ratio we can always make its direction ratio same. So ABC we can make it same, right? And another plane as ax plus by plus cz plus d2 is equal to 0. Then distance between these two planes must be d1 minus d2 modulus of that upon a square plus b square plus c square under root. Okay. Now condition for two planes to be perpendicular. For two planes to be perpendicular. So two planes are perpendicular when its normal vectors are perpendicular, right? So we have normal vector of, say we have plane a1x plus b1y plus c1z is equal to plus d1 is equal to 0, and we have plane a2x plus b2y plus c2z plus d2 is equal to 0, and these two planes are perpendicular. So we have a relation. So normal vectors of these two planes are also perpendicular. So we will be getting, say n1 is the normal vector of this plane and n2 is the normal vector of this plane. So n1 is a1i plus b1j plus c1k, we can always write it like this, and n2 is a2i plus b2j plus c2k. So we will always be getting n1 dot n2 is equal to 0, right? So we have a relation a1 a2 plus b1 b2 plus c1 c2 is equal to 0, such that these two planes are perpendicular, right? Now we have a concept of distance between, to find distance between two lines. Distance between two lines. Okay. Say if we have a two line, this and this. So what are the cases if two lines are in space? Okay. So case 1, lines are intersecting. Okay. Case 2, lines are parallel. Case 3, lines are neither intersecting nor parallel. This case also can happen. So for case 1 and 2, lines must lie on a plane. Lines must lie on a plane. Okay, so two intersecting line or two parallel line always defines a plane, isn't it? Say two lines are intersecting, then they must lie on a plane. Okay, or if two lines are parallel, then they also must lie on a plane. But there is also a third case existing here, such that lines do not intersect and they are not parallel. So those lines are called skew lines. So third case is lines are skew. Okay. So suppose we have to find the distance between two lines. So in first case, distance between these two lines are 0, because these lines are intersecting, and hence we will be getting minimum distance between those two lines is 0. Say if lines are parallel, then there is always a fixed distance between these two lines and we can always find them. Say equation of first line is r is equal to a1 plus lambda b1. Say r1, this is r1, and second line equation is r2 is equal to a2 plus lambda b1. Here we will be writing in both cases b1 because we have same vector in direction of these two lines. So this must be, we can make this same, right? We can make this same because direction ratio or direction cosine of these lines must be same. So we have r1 and r2 like this. If we want to find the distance between these two lines, so basically we have to find, say this is point A, A1, and this is point A2, A2. Say this is, then this vector is A1 minus A2 or A2 minus N, whatever. So basically if we want to find this distance, we have to find the projection of this vector on this, right? That means we have to find, say this is theta, then we have to find distance is modulus of a1 minus a2 cos theta, right? So we have, and we are already knowing this angle. We can already find this angle. Say this angle is phi, so we can already find this angle. How? Since we know vector b, so and we know vector a1 minus a2, so we can always have the value of this angle. So what is this? We can always have cos phi as, say let us take two parallel lines. Say this line is we have two parallel lines, okay, whose equation is r1 is equal to a1 plus lambda b and r2 is equal to a2 plus lambda b. B is same because direction ratio of these two lines are same, okay, and we have a point, say a1 here and say a2 here, okay. Then this vector must be a2 minus a1, and distance between these two lines is d, which is a2 minus a1. D is, say if this vector is d, then a2 minus a1, this vector is d, then I mean this vector is a2 minus a1, then this d must be equal to magnitude of a2 minus a1 times sine theta, right? And what is the value of sine theta? Say a2 minus a1 cross b vector will always give a2 minus a1 magnitude into magnitude of b into sine theta. So sine theta can be written as a2 minus a1 cross b upon magnitude of a2 minus a1 into magnitude of b, right? So substituting here in place of sine theta, substituting this value, we will be getting a2 minus a1 cross vector b upon magnitude of vector b. Taking modulus of this vector will give always positive distance between these two lines, right? So this is the distance between two lines which are parallel. Now how to find the distance between two lines which are skew? So there must be some shortest distance, right? Say this is the shortest distance between these two lines, skew line. Equation of these two skew lines can be written as R1 is equal to A1 plus lambda B1 and R2 is equal to A2 plus lambda B2, right? Here A1, A2, B1, B2 are different, right? Say this is point A1 and this is point A2. So we have this vector as A2 minus A1, right? So we have to find this distance, which is shortest one. If you notice, this shortest distance must be perpendicular to this line as well as this line. Okay. So what is a vector which is perpendicular to both vectors? B1, because B1 is a vector in direction of line R1, and B2, which is in direction of line R2. So a vector which is perpendicular to B1 and B2 can be given as B1 cross B2, right? And unit vector perpendicular to B1 cross B2 can be given as B1 cross B2 upon magnitude of B1 cross B2, right? So we have the project. If we want to find the distance D, then this is nothing but the projection of vector D is nothing but projection of vector A2 minus A1 on vector B1 cross B2, right? So we have already seen what is the projection of two vectors. So its projection can be written as A2 minus A1 dot B1 cross B2 upon magnitude of B1 cross B2. Okay. So this is the distance between two skew lines. Modulus we have taken to get positive value of D, right? So we have almost covered the theory of coordinate geometry, 3-dimensional coordinate geometry and vector. Now we will be solving few problems to make our concept more clear. Okay.